Hi all. In this video, we are going to present a paper titled SSD Single Shot Multi-Box Detector for Real-Time Object Detections. So many object detections are a multi-stage process. For example, proposing a set of bounding boxes, then extracting bounding box based features and using that features in a classification algorithm to classify that particular bounding box to belong to the particular category or not. So this extensive stage line process takes enormous amount of computational overhead during training time and especially on the real time. Faster RCNN alleviates these problems in a certain bit, but it trades off certain accuracy. But still, it considered to be too slow for real-time video object detections. So it only operated fast on PS. We are expecting to operate around like 59 to 60, which is this is what this paper has telling about. So this paper gives you a single neural network architecture where it bypasses all the stages like extracting bounding boxes and extracting the features from those bounding boxes and putting into the classification deep classification algorithm like convolutional neural network for classifying that particular object or not. It completely bypasses the stage line, and it introduces a single shot detector similar to kind of a YOLA we introduced in the previous video, which is faster than compared to YOLO. At the same time, it's more accurate compared to the stage line like faster RCML. So what it does is it is a small variant different compared to the YOLO. YOLO operate on a single feature map. It operate whereas SSD operate at hierarchy of feature map at different scale, and from those different scale at different bounding box are extracted, and then it propagated into the classification algorithm for further regression and the classifications. Through this, it improves multi-stage problem in the image, and also it gives you improvement in accuracy, also improvement in real-time computations, and especially it is well suitable for if the input images is of low resolutions. So this is what the architecture. Some so I'm just going straight away into that, but we will be seeing these descriptions. So whoever have seen the previous video on YOLO, it is like kind of a single image putting into a base network and extracting those convolutional features. And here they operate on different S cross S grid, and from those the filters are operated at this level, and it all extracted here and put it into the detections and non-maximum suppressions and gives at 45 fps, and this is a score for single this single shot detections put up into a base network with certain low deep uh, not compared to like a Google net. It is like an AlexNet, 5 convolutional layer followed by 3 fully network, only 5 convolutional layer or 3 convolutional layer network, I think. So it is like a VGG net. So from that, it has additional few layers of different scales. So through that, it operates those operations which we did it in the faster YOLO have been applied here, and the features are extracted and put it into non-maximum suppressions. Then we get an high accurate with high frame rate. So we will just this is the overall architecture, but we will see this into this descriptions. So what this model says? The model is a single shot detector, like similar single shot as it uses only one feed forward convolutional neural network. It has a two set of layers. One is a base network which has a set of convolutional layers. From that, additional layers of different sizes are added progressively to handle images which contains objects of multiple scales. So we have as a base network. After that, a few layers of different sizes of addressing different multiple scales. So each the added layer of different sizes are called each as a feature layer, which is again discretized into m cross n grids. At each grid cell, similar to like faster RCNN or YOLO. At each grid cell, we operate 3 cross 3 small kernel small kernel to extract a certain set of bounding boxes, and that bounding boxes have been put it into a classifications and regressions in order to identify how much it's matching with the ground truth bounding box size, and how much it is matching with the ground truth object categories. So for each if we have for example, if you have like a number of feature layers are like for example for example 10 to 20 layers. For each layer we have m cross n cells. For each cell we have k bounding boxes. For each bounding boxes we have 4 coordinate plus the classification. So these are the output for the each feature map. So we have some L layer of feature map. We have L into m cross n into k into c plus 4 kind of output, and those parameters will be optimized such a way that the optimization will be similar to like kind of a multi-box or YOLO, like minimizing the regression error and also minimizing the classification error. So training is similar to similar setup like fast RCN and multi-box. That's what is mentioned here, and its propagation is applied, and the strategy training objective as mentioned that it will be for classification error, and this is for the regression error, and this is how much importance to give to the regression error, for the reason that the classification will have high amount of negative samples, and this is similar to kind of assignment problems, which we more detail about this kind of objective function is given in the multi-box video and YOLO video. So this is what strategy in SSD. It's not that much bigger update in comparison to multi-box or YOLO. It's a kind of a clever strategy to address a multi-scale problem. Usually, the multi-scale problems are addressed in two standardized ways. One is put a pyramid of images of different scales, or pyramid of filters, like in deformable part models. But here they have put a different level of future layers, which is been added after a certain number of base layers, and from each future layer been act like an input where a certain kernel of 3 cross 3 is operated at prescribed cells, and from there for each prescribed cell a bounding box is being extracted, a set of bounding boxes extracted, and that set of boundary boxes is extracted to identify the regression error and the classification error. So this all faster RCN and YOLO, SSD, multi-box, all are similar setup. One is the thing is how far the input setup and how far the output setup, how far that sliding window setups are been different, and more importantly how far the training objective is been set, and how those parameters are parameterized, either it is in a hierarchical way or in an alternate way or a single shot way. So those are small key differences between all these algorithms, and once again we will try to see that figure, which will give you a good overall idea about what is this comparison between the SSD and the YOLO. There is nothing much big difference. It's an input image, same thing, but it has a bit higher resolution. It has lower resolutions, and it has a base layer. And it doesn't have a base layer. It operates, that sliding window operates at the pixel level. Here, sliding window operates at the feature level, but the feature levels are different hierarchy of feature levels, and all those feature level output of the bounding boxes are given to the deductions, and then here it gives a non-suppressions to eliminate higher variation with non-positive and negative samples. And this additional setup gives you a higher frame rate and higher accuracy. Yeah, that's all about this SSD. Hopefully, I'll come up with the next video related to focal loss. Thank you.